Bismillahirrahmanirrahim. Assalamu alaikum students. Today I will first discuss the idea of bulk modulus. Bulk modulus and compressibility. Right? You know it from your previous study. I just remind these ideas or refresh these ideas because I need them. How we define bulk modulus? When a body is submerged in a fluid such as water, for example, let there be some container and inside this container there is water, can be any fluid, water, or we can talk in terms of any fluid. And you know fluid includes liquids as well as gases. When we say fluids, that means liquids as well as gases. So suppose we have a body, some body and V is the volume of the body. Right? So when I place this body in some fluid such as water, as I have shown, there is an increase in pressure on the body due to the fluid pressing against the body, which tends to compress the body. I repeat, when I place this body inside the water, or I can place it any fluid, what happens? There is an increase in pressure due to the fluid pressing against the body, which tends to compress the body. Let delta P be that increase in pressure on the body. Increase in pressure on the body, right? What will happen? This increase in pressure will tend to compress the body. That means its volume will decrease. Let delta V be the change in volume of the body because of this increase in pressure. We know this change in volume of the body will be negative because all bodies compress due to increase in pressure on them. Now, what is delta V by V? This delta V by V is fractional change in volume. Delta V is change in volume, V is its original volume. So this delta V by V we call fractional change in volume of the body. Fractional change in volume of the body. Since here it will be negative, delta V will be negative, so it will be, when we take that thing into consideration, it will be fractional decrease in volume of the body. Now, the bulk modulus of this body by definition, bulk modulus is actually the bulk modulus of the material of the body. This bulk modulus is material specific. So bulk modulus B of this body is defined as the ratio of the increase in pressure, that is delta P, to fractional decrease in volume, right? So in symbols, I can write delta P over delta V by V. Delta V by V is fractional decrease in the volume. Delta P is increase in pressure. Now, in this definition, we write here minus. Why? Because we know all materials decrease in volume when they are subjected to an increase in the external pressure. So this delta V by V is going to be a negative quantity. In order to make bulk modulus positive, we write here 1 minus within this equation, right? So this minus sign in equation 1 is introduced to make B positive. What about SI unit of B? It is simply same as pressure because denominator is unitless, that is Newton per meter square is the SI unit, force per area, or which we call Pascal. So Pascal or Newton per meter square is the SI unit of bulk modulus, right? Now we specify materials by bulk modulus. What does it indicate? It indicates if we increase pressure by some amount, what is the fractional change in volume in the body. So larger bulk modulus will indicate smaller change in volume, or I should say smaller fractional change in volume for a given change in pressure. So if your body has larger bulk modulus, by that you will understand if I increase pressure by some amount on this body, its fractional change in volume, which is fractional decrease in volume, is going to be smaller. If bulk modulus is smaller, that in other words means it is easier to compress the body, right? Because you need smaller pressure if B is small, right? Now the inverse of the bulk modulus, the inverse of the bulk modulus is called compressibility. It is denoted by K. So compressibility is 1 over bulk modulus, which is minus delta V by V over delta P. So this is defining equation of bulk compressibility. Simply I have to reciprocal the bulk modulus, so I got compressibility, right? Now the concept of bulk modulus and compressibility can be applied to liquids and gases as well as solids. Now, solids and liquids are relatively incompressible. That means it is difficult to compress solids and liquids. Therefore, they have, or that is indicated by the fact that they have small values of compressibility or large values of bulk modulus. I write solids and liquids have solids and liquids, as they are relatively incompressible, they have small values of compressibility, small values of compressibility K or large values of bulk modulus. Solids and liquids, I repeat, are easy to compress. Solids and liquids are relatively incompressible. They are difficult to compress. That means they have small values of compressibility K or large values of bulk modulus B. And these values are relatively independent of temperature and pressure. Gases, on the other hand, they are easily compressed. So, and their values of B and K depend strongly on pressure and temperature, right? So for gases, K will be large and B will be small, right? The reverse of solids and liquids, because they are easy to compress. This was one topic of today's lecture. Next thing, which is very important, we have to discuss the mathematical properties of state functions. Mathematical properties of state functions. Now we have already discussed certain state functions like internal energy, U, entropy, S, and some non-state functions, which are also called path functions. Path functions are those functions which are not state functions, like heat, Q, work, W. They are not state functions. So these are state functions. These are not state functions, that is path functions. They are path functions. Now our discussion of this particular concept, which I have under this heading, the mathematical properties of state function, is only applicable to state function, like internal energy and entropy, right? Our discussion will not apply to path functions like work or heat. Let us start our discussion. We know for an ideal gas we can write PV is equal to nRT. Let me use another color. So PV is equal to nRT. Now consider N is 1 mole. So if we have 1 mole of an ideal gas, then N is 1, we get PV is RT. Now remember, pressure, temperature, volume are also state functions, right? So I can write P equal to RT by V, right? So pressure, R is constant, is function of temperature and volume. Therefore, I can write P is function of volume and temperature, which is equal to RT by V. Let me name it equation first. Note, pressure P can be written as a function of two variables, as you have seen in this equation, volume and temperature. Therefore, the change in pressure resulting from a change in volume or temperature can be related to the following partial derivatives. Which partial derivatives? If I write dou P by dou V at constant T, means mathematically limit delta V tending to 0, P V plus delta V T minus P T over delta V. What is dou P by dou V at T? It means I partially differentiate pressure with respect to volume, keeping temperature constant, and mathematically that means I have to give increment only to volume. T is constant. So when I partially differentiate equation 1 with respect to volume, keeping temperature constant, what I get is elementary differentiation. I get minus RT by V square. Now I differentiate pressure with respect to temperature, keeping volume constant, because pressure is depending on two variables from this equation, volume and temperature. So it's a multi-variable function, and in case of multi-variable functions, we talk of partial derivatives in order to see change in that particular quantity, here pressure. So now I differentiate pressure with respect to temperature, keeping volume constant. Now let me use another color for volume, keeping volume constant. So mathematically that will mean I have to give increment to temperature. So it is limit delta T tending to 0, P of V. C, I will give now increment to temperature. T plus delta T minus P Vt over delta T. So increment is in temperature. So when you do that, you have expression before you RT by V. Now you differentiate it with respect to temperature. You will get just keeping V constant, it is just R by V. Right? It is just R by V. Right? Now what is the change in P? You know that when you have to write or change in some function, change in any function is proportional to the derivative of that function. Therefore, if pressure changes from P to D, P plus dP, or let me state this way, what is the change in pressure P if the values of T and V both change? How to write that or find that? What is the change in pressure P with the values of T and V both change? We write it this way. dP is equal to dou P by dou T, dou P by dou T at constant V dt plus dou P by dou V at constant T dV. This is how we write change in pressure. We write dP is equal to dou P by dou T at constant V times dt plus dou P by dou V at constant T dV. Right? Dou P by dou V at constant T dV. Right? Let me name these equations. This was my first. This is my second. This is my third. This is my fourth. Right? Now in this equation, in order to find the change in pressure, we need first partial derivatives, and we need to know by how much temperature changes and by how much pressure changes, right? And this expression is valid only for small changes in pressure, because for small changes, these partial derivatives are constant. For larger changes, we have to take the variation of the derivatives into consideration, and for those changes to calculate, we have to use second order derivatives also, right? Now, consider the case of mixed second partial derivatives. What is mixed second order partial derivative. See what I write here. Idea of mixed second partial derivative. Mixed second partial derivative. C. If I write dou P by dou V at constant T, then dou P by dou T at constant V, this is written as dou 2P by dou T dou V. What is the meaning of this? Meaning of this is, first we find the partial derivative of pressure with volume, keeping temperature constant. Now the result which we get, we differentiate that with respect to temperature, keeping the volume constant. So first we differentiate with respect to volume, keeping temperature constant. Then the result, that is first order derivative, is differentiated with respect to temperature, keeping volume constant. Now if you do that, you get minus R by V square. We get minus R by V square. If you use this equation, you have found the first derivative, first partial derivative of pressure with respect to volume. That's minus RT by V square with respect to volume, keeping temperature constant. Then I have to differentiate it with respect to where is this? With respect to temperature, I get minus R by V square, right? Now, if I reverse the order, that means I do dou P by dou T at constant V, then I differentiate it with respect to volume, keeping temperature constant. I write dou 2P by dou T dou V. Because dou P by dou T at V, I differentiate it with respect to volume, keeping temperature constant. It is dou 2 by dou 2P by dou V dou T. It is also minus R by V square. Operation is different. See, here I am first partially differentiating pressure with respect to temperature, keeping volume constant. Then the quantity which I get from that, I differentiate that with respect to volume, keeping temperature constant. That is, first I differentiate pressure with respect to temperature partially. Then I differentiate the resulting quantity with respect to volume. I get minus R by V square again. So here, this called mixed second order partial derivative, because first differentiation is with respect to one variable, second differentiation is with respect to another variable, right? In first differentiation, second variable is held constant. In second differentiation, first variable is held constant. Now here we are seeing this order of differentiating pressure with respect to volume or temperature is not affecting the result, right? This is true for all state functions F. I write for all state functions F, and for our specific case of P, the order in which the function is differentiated does not affect the outcome. I repeat, for all state functions F and for our specific case of pressure P, the order in which the function is differentiated does not affect the outcome. For this reason, I can write dou by dou V of some function of Vt, keeping temperature constant, then differentiating that with respect to T, keeping volume constant is same as dou by dou T of some function Vt, keeping volume constant, then differentiating that with respect to volume, keeping T constant. Dou by dou V of F Vt, keeping T constant, then differentiate that with respect to temperature, keeping V constant is same as differentiating this function with respect to temperature, keeping volume constant, and differentiating the result with respect to volume, then keeping temperature constant. I name that equation as this is my 4, this is my 5. Now, because equation 5 is only satisfied by state functions F, it can be used to determine if a function F is a state function. So it is used, this property of mixed second order partial derivatives satisfied by state function is used as a test. It is used as a test. If this property is satisfied by a function, that order of differentiating the function doesn't affect the outcome, we can say this function is a state function, right? And you know, any state function F can be expressed as an infinitesimal quantity, df, that when integrated depends only on the initial and final states. That means I can write for any state function, its finite change can be written as integral df I to f, where df is infinitesimal change. Then I can write it f final. Sorry, let me clear it first. Use another color. F final minus f initial, right? And df is called an exact differential. This df is called an exact differential, right? There are two other important results from differential calculus which will be used by us in coming lectures frequently. What are those important results? Consider a function z equal to f of xy, which can be rearranged to x equal to g of y and z, another function, or y equal to h of xz. For example, if P is nRT by V, then V is nRT by P and T is PV by nR. Now in this case, I repeat, we have a function z equal to f of xy, which can be arranged or rearranged to this way that it can be written, expressed as function of yz, x as a function of yz, or y as h, another function which I will represented by h of xz, and or another function. So we can express this function either in terms of xy, yz, or xz, right? For example, if pressure is expressed as nRT, written as nRT by V, then it is expressed as function of TV. So we can write V equal to nRT by P. That means volume can be expressed as function of temperature and pressure. Also, temperature can be expressed as function of pressure and volume, because you can write from this equation T is equal to PV by nR. Now, in this case, dou x by dou y, keeping z constant, is equal to reciprocal of dou y by dou x, keeping z constant. Let me encircle it. This is a property. You have to remember it. This is my equation 6. Equation 6 was 5, it is 6. I'm saying I can derivative of x with respect to y partially, keeping z constant, is reciprocal of, you reciprocal this also. Dou y by dou x, keeping z constant. We can apply another thing, which is called cyclic rule for such functions. The cyclic rule can be used. What's a cyclic rule? Cyclic rule. You can write dou x by dou y, keeping z constant, then dou y by dou z, keeping x constant, multiply that by dou z by dou x, y constant, and this product is equal to -1. This identity, this rule, is called cyclic rule. I named it equation 7. What I'm writing dou x by dou y, partial derivative of x with respect to y keeping z constant times partial derivative of y with respect to z keeping x constant times the partial derivative of z with respect to x keeping y constant is -1. So I stop here. I will continue with this. You need to remember these things. I summarize a bit. Our topic was, besides what we discussed in the start, bulk modulus and compressibility, that was very obvious kind of thing. Then we discussed properties of state functions. We said that there are some functions which are state functions like internal energy, entropy, some other functions which are not state functions, which are called path functions. And now we developed certain rules for state functions. For that, we took an ideal gas. We said let it be 1 mole. So we can write pressure as function of volume and temperature, which is RT by V. Then we found these partial derivatives of pressure with respect to volume, keeping temperature constant, which turned out to be minus RT by V square. Then we differentiated pressure partially with respect to temperature, keeping volume constant. It turns out to be R by V. Then we said if the temperature and volume both change, how can we write the change in pressure? So we wrote this expression and we said this is valid only for small changes. Otherwise, these first order derivatives will change as temperature and volume changes. And we need to take into consideration their change also. So it is valid only for small changes. Then we talked of the mixed partial derivatives. We said that if we differentiate pressure with respect to volume with temperature, then with respect to temperature, we get minus R by V square. If we reverse the order of differentiation, first differentiate with respect to temperature, then with respect to volume, we get the same result. Then we generalize this equality of mixed partial derivatives for all state functions. We said it is true for all state functions f, and we then said that since this is only true for state functions satisfied with state functions, this equality of mixed second order partial derivatives, so it can be used as a test. We can use it as a test for a function to test a function whether it is a state function or not. So then we said a finite change in a state function can be written as infinite change in the function. Then we can integrate that infinite change in the function from I to f. It will be the value of the function at final state minus the value of the function in initial state. df is called an exact differential, and this nomenclature of exact differential is used only for state functions, right? And we said if we have such kind of function where you can switch your variables like this, you can express z as function of xy or x as function of yz or y as a function of xz, then you can use properties expressed by equation 6, and you can use also cyclic rule expressed by equation 7, right? So this is all for today. Thank you. God bless you. Assalamu alaikum.